We learned one that looks like this and one that looks like this. Which of these is the parent function for this problem? The one on the right, right? So this was the parent function for 1 over x, and this one was 1 over x squared. However, because of this negative in front, what does that mean is going to happen to the parent graph? It's going to flip. It's going to reflect over the x-axis. So I'm going to draw that in red on the exact same graph, okay? So you can see that they're two different things. Right? So now what the problem is asking you to do is two things. Draw the new graph of that red stuff that's been shifted. The origin goes to 2, 3. So which way am I going to shift that graph? Which directions? Right and up. Okay. And then I'm going to write the equation for it. So if you don't remember how to do that, or you didn't get to the homework, here's the general form for the equation. It's -1 over x squared, but that x now has the h with it, the insiders lie, and that's squared. And then the k goes on the outside. Where am I going to get that hk information from? The point, the shifted origin, which is 2, 3. So this is your h, and this is your k. You're just going to plug those in. I mean, that is literally all you're doing, is plugging in 2 for h and 3 for k. Right? So take 60 seconds to finish that out if you needed that sort of help to get started, and then we'll talk about it. Okay, so here's what's up with today's lesson. I'm about to throw a whole bunch of information at you, okay? And you're going to get frustrated, okay? Maybe, probably, most of you. But here's what I want you to do. I want you to just breathe, and I want you to just trust me. Write down everything I write down, even if you have no idea why I said what I said, and then you think it's all just nonsense and magic. Just write it down. We're going to practice this for several days so that you can get it. And once we do it several times, you'll get the hang of it. It's just that it's a very long process just to do the one problem, okay? But you're not dying today, okay? Not from math anyway. It's not going to be my fault. So are we breathing today? We're just going to be calm and write down everything, and we're going to be okay even if we don't understand. We're just going to tell ourselves, I don't have to understand today because Ms. Ev said I don't have to. All right? Okay. So what you have here, so here's the point of today's lesson. We want to graph a function, right? We've graphed stuff before. We've graphed linear equations, y equals mx plus b, right? And then we upped our game a little bit, and we learned a bunch of parent functions, like cube root and cubed, and we graphed transformations of those. We flipped them, we reflected them, we did all those things. Rational functions, which we started talking about yesterday, work differently, all right? Remember we talked yesterday that rational functions are things that look like fractions, but specifically they have variables in the denominator as well. And so that yellow sheet you have there, your SHRATEY sheet, it's an acronym, okay, SHRATEY, however many things that is, 7 or 8 letters. Each of those is a little step for gathering information from the function that will help us graph it, all right? So that's the whole point of that yellow thing, and it is a long process, but with practice it becomes easier. And the first thing I want you to do, though, is change the function on your notes to this one. I feel like this one's better because it hits more concepts. So this, I know it's hard to see, so I'm going to write it up here real big. X squared plus 3x over x squared minus 2x minus 3. We're going to take your SHRATEY acronym one letter at a time to collect information, and then use all the information to sketch out a graph of the function. I feel like there's something else I wanted to say. I don't know. The very first step is S. According to your SHRATEY cheat sheet, what does that stand for? Okay, simplify the equation. So if I were to ask you, if I give you some easy fraction like 12 over 4, and I said simplify that, what would you tell me? 3. What did you do to the 12 and the 4 to get? You divided it by a common factor, something they had in common. That's what we're going to do here. It's just that when there's x's everywhere, in order to figure out if they have a factor in common, we have to factor it. We have to factor the top, and we have to factor the bottom. This is where we use our GCF, difference of two squares, swing method, all that good stuff, all right? So we're going to factor the top and bottom to see if we can even simplify it. So look at the top. I've got x squared plus 3x. That's a GCF. What's the GCF that I can factor out? All right. So I'm not just going to get rid of the x. I'm just going to write it down, and then what goes in parentheses? X plus 3. Okay. So I have factored the numerator, okay? And that's right here on your cheat sheet. You're not going to forget to do that because it's right there. It says factor the numerator if possible, and then factor the denominator if possible. Looking at the denominator at the bottom, what method will I use to factor that? Swing, okay. What multiplies to negative 3 and adds to negative 2? Negative 3, positive 1. And technically we should divide off by the a value, but that's just 1, so it doesn't change anything. So I take that negative 3 and that 1, and I use them to write factors for the denominator. And none of those factors can be further factored, so we're just going to leave them as they are. And the last part of the S step says, cancel any factors that occur in the numerator and the denominator. Do you see anything like that? No. So nothing cancels out here. So S, done. Okay, I factored the top, factored the bottom, looked for stuff that canceled, nothing cancels. What does H stand for? Holes. Holes come from any factors that canceled. Did we cancel anything? No. So our graph doesn't have any holes. So we're going to put NA. And when we do get to holes, or it's just a shorter name for discontinuities, which we'll talk about later in the unit, it's really just an open circle somewhere. It's like literally a hole in the graph. Okay, so we're done with that. What does R stand for? Roots. What are roots? Are those points? Are those lines? What are they? They're x-intercepts. They're solutions. What do they look like on a graph? A point or dots, right? They're points. And so right here where it says roots, what does it say after roots? It says what? Solution to the top. You're going to take the top, whatever you factored out in the numerator, you're going to solve it. Well, that has to look like an equation. It does not look like an equation right now. Here's the top. In order to solve x for the intercept, you do what? Set it equal to 0. So R stands for roots. That means you take the top and you set it equal to 0. Okay. And then you're going to solve for each of those x's. Well, just like in the past when we used factoring to solve, we take each of these factors and set them equal to 0. And that gives us these little mini equations. That's our zero factor property. Okay. Because I have two things multiplied give me 0, so one and or the other has to equal 0. So that first one, x equals 0, I can't do anything more with that. That's just there. But the second one, I can subtract 3 from both sides and solve. I get x equals negative 3. So if you're looking at the R section, okay, it says these are x-intercepts, set the numerator equal to 0 and solve, and then it says write the answers as what's? What does it say on your sheet? Under R? Points. Some number, comma, 0. And the reason for that is because if I left it in this form, these are equations of lines, okay? They're not points. These are points. 0, 0, and negative 3, 0. Right, so I have two roots for this function. I'm going to go ahead and put those on my graph. 0, 0, and negative 3, 0. So R is for the roots. You let the top equal to 0. The next thing is for letting the bottom equal 0. And what that gives you is asymptotes. All right, so we're going to let the bottom equal 0. I've got x minus 3, x plus 1. Same process. I'm going to set both of those factors equal to 0 individually. And on this step, I'm not writing it as a point. I'm going to keep it just like it is because it actually represents a line, and I'll explain to you why there's a difference. On the R step, when I set the top equal to 0, the reason why I'm doing that is if the top equals 0, the whole thing equals 0. The whole thing represents your output, your y value. So when x is 0, then that would give you, I'm sorry, not when x is 0. When you set the whole thing equal to 0 and solve, you're getting y equals 0 for both of those. Those are literal points. But when we're setting the bottom equal to 0, we're finding a different thing because we don't want the bottom equal to 0. Remember, that is undefined. You can't take something and actually divide it into 0 pieces. So what we're doing when we say, okay, x equals 3, we're saying if I put 3 in right here, put 3 in there, okay? That gives me 3 minus 3 is 0. And what happens when I multiply that by this thing? I still have 0 on the bottom. It's bad. So what that is telling me is x cannot be 3, ever. Well, how many places could x be 3 on a graph? It could be 3 here, but also here, and 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 here. Okay, x can never be 3 no matter where it happens on the graph. So that's why it's an equation of a line. And it's an imaginary line, because it can't actually equal 3. It's what we call an asymptote. So what I'm going to do for this line is fill it in like this. It's really just a placeholder telling me the graph will never, ever, once I get to the graphing part, will never, ever, ever cross that line. Because x cannot ever actually be 3. So that's why on this step we have equations that are lines, and on this step we have answers that are lines, and on this step we have answers that are points. And then we have another asymptote at x equals -1. So it can never, ever, ever be equal to -1. So we simplified the top by factoring the top and bottom. We have no holes because no factors canceled. We found the roots by setting the top equal to 0. We found the asymptotes by setting the bottom equal to 0. And the next thing we're going to do, T, is something really kind of new that doesn't really just flow from anything we've done yet this year. If you look at the back of your sheet at the T section, what is that main concept right there? Say. Special square, but right here and before, what does the T stand for? Tangent together. Now, if you notice, that's written tangent over together. It's written like a fraction. That's on purpose, all right? That's not like just a space saver or something. It's because the tangent piece is talking about the roots, which comes from the numerator, the behavior at the roots. And the together piece is talking about the behavior at the asymptotes. That information comes from the denominator. So there's a reason it's written like a fraction. So the tangent part is the behavior at the roots. And the together part is the behavior at the asymptotes. Okay? And what I just wrote down is also on your sheet, tangent at the roots or together at the asymptotes. Now the tangent at the roots part actually is something that we did talk about last semester. Tangent, the word tangent means, like if, you know when you're talking and someone goes off on a tangent, right? They go off in some other direction than the original topic. Okay, same thing here. If the graph is going off at a tangent at the root, it's bouncing. That's the vocabulary we used last semester. We say it bounces at the root. And if it didn't bounce, what did it do? What was it? It crosses. So this step right here is giving me that same kind of information. Is the graph going to bounce at the root, or is it going to cross through? What was our clue about that last semester? What told me whether it bounced? Odd or even exponents, okay? We're looking at the multiplicity of the factor. If it's even, it will bounce at the root. If it's odd, it will cross through at the root. So looking at this particular problem, where am I getting this root information, the numerator or the denominator? Numerator, right? So I'm going to go look at my factors in my numerator. I have two factors. I have x and I have x plus 3. Those give me two different roots. Is the x squared or to the 4th or to the 6th or anything even? No. So the root that gave me was 0, 0. It's going to cross at that root. X plus 3 gave me this other root. Does it have an even multiplicity? The x plus 3? No, right? It's not squared. It's not to the 4. It has an odd multiplicity. So I know the graph is going to cross at that root. So here on my t step, I've only talked about the root information. I'm going to write this. I'm going to write, no, it's not tangent. That means it's going to cross. Okay, I'm just giving myself some notes here. I'm going to use this information, not yet. I'm using it in a bit. It's just going to kind of hold out here. So this t-step, I'm looking for if anything is squared. If it's squared, it bounces at the root. If it's not squared, it crosses. Okay. Now let's talk about the denominator information, the asymptotes. Same thing. I'm looking for whether or not the factors are squared. So if I go back to my original problem, I have two factors, x minus 3, x plus 1. Okay. Are either of those squared? No. Here's what squared means for asymptotes. And don't write this down because I'm going to erase it. Squared for roots means bounces. Squared for asymptotes means it comes together, which means on either side of the asymptote, it comes together in the same direction. Or on this asymptote, maybe if it was going down, they'd be going down. This means coming together. Okay, that's if it's squared. Okay, our problem, there's nothing squared. So if it's not coming together, then it's going opposite. So if I say no here, no, because there's no squared factors. That means instead of coming together, it's going in opposite directions. Meaning instead of both going down, one's going down, one's going up. Okay, and I just want you to hold that information, and I'll show you specifically what that means when we graph this in a bit. So if there's nothing squared, that means it's going opposite instead of together. E stands for end behavior. Okay, we talked some about that yesterday. End behavior means the behavior of the graph at the ends. Okay, it means way out here to negative infinity, and what's the behavior way out here to positive infinity. And what this piece is going to give me is my horizontal asymptote. Okay, we just did two vertical ones, and now we're going to find the horizontal one. So if you look at the E part of your notes, there's a table there. I want you to X out the middle of the table. We won't be doing kinds like that. We'll only be doing balanced equations, which is on the left of the table, and bottom-heavy equations, which is on the right. And what does it say right after end behavior in the bold type? There's E, there's end behavior. What does it say next? I want you to look at it with your eyeballs and tell me what it says. Look at leading terms. Here's what that means. You're going to go back to your original equation, not the factored form, but all the way back to the beginning. And you're going to look at the leading terms. What do you think is the leading term in the numerator? The leading term, if it's leading, it's in the front, right? So what's the leading term up top? X squared. And what's the leading term on the bottom? Okay, so you're looking at the degrees. The degrees are the highest exponents. If they're the same, that's balanced, right? Because they're the same, they're in balance. A bottom heavy would mean, what do you think? They're different, and which one would be bigger? The one on the bottom, right? In this particular case, they're the same. So we have which kind, balanced or bottom heavy? Balanced. And here's how we use that information to find our horizontal asymptote. We make a ratio of the leading terms, and we simplify it. What is x squared divided by x squared? Okay, it's 1. That is my horizontal asymptote. So if you're looking at your end behavior section, right here under balanced, it says write it as a line. Y equals whatever your number is that you came up with. Okay? So it's going to be y equals 1. But what does this whole section stand for? What does E stand for? End behavior. So even though this is a horizontal asymptote, and even though I'm about to go draw it in all the way across, just like this. Actually, I'm going to do a different color and see. I think that'll help. There's a special thing about this asymptote. It only is modifying or influencing the behavior of the graph at the ends. So as I'm going out to negative infinity, whichever way my graph is going, it's approaching the line but not crossing it. Way out here at the end, it's approaching the line but not crossing it. It is possible and okay for your graph to cross that red line somewhere in the middle, because the middle is not the end. Okay, so the horizontal asymptote is just determining end behavior. So black asymptotes, absolutely the graph will never cross, ever, 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 not even once. There's no special case. Keep in mind that the red asymptote means it's determining end behavior. Now, in the past, I've tried erasing the middle, like not having it there, so hopefully as like a visual to remind people, but then what happens is people forget about it altogether. So I'm going to keep the line all the way across. If that messes with your head, you are welcome to erase the middle as a visual indicator that you can cross that boundary in the middle. Okay? And that is something we will go through with each new problem, and I'll remind you over and over till you remember. All right. So that was E for end behavior. We have one last thing, and it's easy. Y stands for what? Y-intercept. And what is a y-intercept? What does x always equal at the y-intercept? 0. So all you have to do here is plug x equals 0 and solve for y. We happen to already know what it is. What is it? No. When x is 0, what is y? 0. That won't happen like that every problem, but in the case that it wasn't like that already, you would just plug in 0 for x and solve your original equation. You'd get 0 for y. So what we've just done is gathered a whole bunch of information, and now we're going to Sherlock Holmes this problem and try and figure out what the graph is going to look like from all these clues that we've gathered, right? So here's what we go. So we have all this stuff. And we have a framework beginning over there. Our job is to figure out how to fill in all the pieces. These vertical asymptotes right here break my graph up into 1, 2, 3 things, right? So I have to figure out all 3 of those pieces. How are they going to look? How are they going to play together, and where is everything going to be pointing and all that kind of stuff? So I like to start from the left and go left to right, keeping all this stuff in mind as I go. So if I'm starting here, I have, on the left side, I have this point, but what I don't know is how to start drawing my graph. Don't write this down because I'm going to erase it, but these are like a couple options I have. If I know the graph is going through this point, maybe I could do this. Maybe it goes like that. Maybe it goes like this. Could do that. Maybe I'm thinking it could go like this. Right? So it feels kind of tricky when you're starting these problems. You're like, I can think of 1,000 ways to begin. I'm not exactly sure what to do. But this is where we use our information that we have here. Here's some additional information I have. I know that way out here on the side, that the graph is going to be approaching this red line, either like this or like this. Because that's what end behavior does. That's exactly what that red line is for. So as it goes to negative infinity, my graph is going to be approaching it. It can either approach it from the bottom or the top. So it's got to be one of these 2 things. But because of where this dot is, I really only have one choice. Which choice? The bottom one. Okay? Do you want me to explain that again? Because it feels a little bit like voodoo nonsense, like I'm just making up stuff. No, you're good? All right. Because of that red line, because as it goes to negative infinity, I know the graph is going to approach that red line. It's either got to approach it from the top or the bottom. Because of this dot, I know it's got to be from the bottom. So this is not an option for me. Okay? And that's what I mean about using you've got to use all the information. And the other thing is that for each problem is different. So I can't just give you one method and be like, okay, do that for the next 20 problems. You have to think about it fresh for each new thing. All right, so my end behavior here and my point here, I know it as x goes to the right, I can never cross this line. So as it gets closer and closer, it's just going to be approaching it like that. Okay, so this is my first part done, sketched out. You okay so far? Okay. So now I need to, x, I'm going to keep going to the right to figure out how to sketch out my graph. Now I'm looking at this next interval. Okay, some information I have here, I have this point. Remember that this red horizontal asymptote, in the middle, I can cross it if I need to. Okay, it's okay to cross it in the middle of the graph. My job now is to figure out, well, and I actually know one other thing about the root. Is the graph going to be crossing or bouncing at that root? Crossing. So there's really just two ways it could cross through there. It could either go like this, or it could go like this. So we have to use some of our other clues to figure out which way it's going to go. So if I go here, I'm going to use this T information, because right here is my asymptote stuff. It is not going to come together at the asymptote. Remember I told you that coming together looks like this if it's going down, or it looks like this if it's going up. If it's not coming together, it's going, if it's not doing this, it's doing this. Okay, or it's doing this, it's going opposite. And so I know, here's what that looks like on the graph. So that T information for your asymptote is only talking about what happens immediately on the left and immediately on the right of your asymptote, what that behavior looks like. So if I have this asymptote here, and it's going down, and it's got to go opposite on the right side, what's the opposite of down? Okay, so I'm going to put that arrow there. It has to go up on that side. If the factor that gave me this asymptote had been squared, I would have said, yes, it comes together, and I would have put an arrow here. All right? But it wasn't squared, so it's not coming together, it's going opposite. That's why that arrow up there is going to the top. Okay, do you feel good about that arrow? Okay. So now I have to pass through the 0, 0. It is not going to bounce, because we already figured that out. It's going to cross. And it's going to keep going, the x is going to keep going to the right. And it's going to approach that asymptote. Okay, so now I've gotten to my second asymptote. That factor that gave me that asymptote was not squared, so it's not coming together. It's doing the opposite. So if it's going down on the left side, what's it going to be doing on the right-hand side? Going up, okay, because that's the opposite. So on this third part of the graph, so now x is going out to infinity. There's no more asymptotes to break it up. This horizontal asymptote, now we're talking about that again. As x goes off into infinity, the graph is approaching it from above, and it's going to be getting closer and closer, but never crossing it. So how do you think we can fill in the gap between those two arrows? I can't just go straight because it's not linear. It's more of a smooth transformation. It's going to be like that. So did anybody die? Close? A little bit? Your soul, kind of. I'm going to give you the homework. You're welcome to try it. I think I've made the executive decision to push off tomorrow's lesson and just work on this tomorrow. So if you don't even want to do the homework this evening, you'll be fine because we're going to work on it in class. If you do want to do the homework, I'm cutting off 61 and 65. The last two.